Hello everyone, I am Shabnam Tadga from BSc 5th semester. My combination is chemistry and mathematics. My assignment topic is vibrational Raman spectroscopy. Vibration rotational Raman spectra means rotational fine structures complementary of Raman and IR. First we discussing about introduction of Raman spectroscopy. Raman spectroscopy is a powerful technique based on the Raman effect discovered by C.V. Raman in 1928. It involves the inelastic scattering of monochromatic light, usually a laser, by molecules, resulting in a frequency shifts corresponding to molecular energy transitions. Vibrational Raman spectroscopy provides information about the vibrational energy levels of molecules and it complementary to infrared spectroscopy. Infrared means IR spectroscopy. First we are discussing about vibrational Raman spectroscopy. Vibrational Raman spectroscopy is when light interacts with molecules. Most scattered light has the same frequency as the incident radiations, and a small fraction of scattered light shows frequency shift due to absorption or release of vibrational energy quanta. And Stokes lines photon losses energy molecules excited to higher vibrational state. Anti-Stokes lines photon gains energy molecule relaxes from an excited vibrational state. Thus a Raman spectrum contains Rayleigh line center Stokes and anti-Stokes bands. This is a vibrational Raman spectroscopy. Next we are discussing about vibration rotational Raman spectra. Vibration rotational Raman spectra is a molecular vibrations are usually accompanied by rotational transitions. Therefore, the Raman spectrum of a vibrational transition is not a single line but a group of closely spaced lines. Rotational fine structures. Rotational Raman selection rules are for a linear molecule delta z equal to 0 plus or minus 2, delta z equal to plus 2 is a S branch, it means Stokes sides. Delta z equal to minus 2 is a 0 branch, it means anti-Stokes sides. This is a different from IR where delta z equal to plus or minus 1. In polyatomic molecules, vibrational transitions are often accompanied by rotational transitions. Therefore, each vibrational Raman band shows rotational fine structures similar to vibration rotation spectra in IR. Selection rules for rotation in Raman depend on whether the molecule is linear or non-linear. This is about vibration rotational Raman spectra. Third one is rotational fine structures. Rotational fine structures are each vibrational transition gives rise to multiple Raman lines, means fine structures. These appear symmetrically on both sides of the Rayleigh line, means incident frequency. The spacing between successive lines equal to 2b or 4b depending on the branch. This fine structure help determine bond lengths and molecular symmetry. Raman transition, the rotational quantum number J changes according to the rule delta J equal to 0 plus or minus 2, delta J equal to 0 Q branch if symmetry allows, delta J equal to plus 2 S branch Stokes sides, delta J equal to minus 2 is a 0 branch means anti-Stokes sides. This is a different from IR spectroscopy where delta J equal to plus or minus 1. Next, energy expression. The rotational energy of a rigid diatomic molecule is given by Ej equal to B into J of Z plus 1. This is about rotational fine structures. B is a rotational constant for Raman transitions. The frequency difference between successive lines in a branch is approximately 4b. This is rotational fine structure. Next we discuss spectrum features. Center Rayleigh line unshifted. Stokes Raman lines means shifted to lower frequency. Anti-Stokes Raman lines means shifted to higher frequency. O and S branches produce equally spaced fine lines reflecting the rotational structure of the molecule. This is the spectrum features. Fourth one is complementary of Raman and IR. IR means the infrared spectroscopy. Infrared and Raman spectroscopy are two complementary vibrational spectroscopic techniques. Vibrations that involve a change in dipole moment. Second one is Raman active vibrations. Vibrations that involve a change in polarity and complementary rules. Some vibrations are active in IR but inactive in Raman and vice versa. Homonuclear diatomic molecules RH2, O2, N2 have no permanent dipole moment. They are inactive. IR but active in Raman. Molecules such as CO and HCl are IR active but often weak in Raman. Hence, both Raman and IR spectroscopy are used together for a complete analysis of molecular vibration and structure. We studied applications. First one, determination of bond length and bond strengths. Second one is identification of functional groups in organic and inorganic molecules. Third one, study of molecular symmetry. Fourth one, analysis of homonuclear molecules that are invisible to IR spectroscopy. Fifth one is widely used in a chemical, biological and material science. Next, last we will discuss conclusion. Vibrational Raman spectroscopy reveals both vibrational and rotational properties of molecules. It is a rotational fine structure. Delta J equal to 0 plus or minus 2 helps determine molecular constants. Raman and IR are complementary techniques, together giving a complete structural information. This is all about vibrational Raman spectroscopy, vibration rotational Raman spectra, rotational fine structures, complementary of Raman and IR. Thank you.